Hello and welcome to this lecture on bitwise operators. What are bitwise operators? Bitwise operators are just like our arithmetic operators, except that we perform manipulations or evaluations of bits instead of actual arithmetic things like multiplication, addition, and so on. So these include things like the and, or, XOR, not, left shift, right shift. So these may seem a little weird to you at first, these names, but we'll go through each one and explain exactly what it does. So in order for us to kind of understand what is going on with our bits, we need a convenient way to print out binary. I've provided you with a binary.h file within the lecture. This is it on the right exclusively. So if you wanted to type this on your own, you can. But again, there'll be a file provided with this information, this function inside of it. So on the left is how to use it, and in the center is the output for this file. You should all you should have to do is include the header file, and it will again replace this text with this text on our right at the top. And if you do not recall what the include statement does, I suggest reviewing the preprocessor lecture. Now, the first operation that we're going to talk about is the AND operation. You can see in the center that we have a truth table. This truth table will list out our inputs and outputs. Our X and Y are input, and this AND symbol here, this is what it's denoted as, is a ampersand, and this is our output section. So you can see that it requires two inputs to be on, so that is 1, to have an output of on. If any is off, it is going to always be off. And you can see that when we have a series of bits and we AND them together, we go one by one, and we AND the first value, which is 1, and then this is 0 because 1. If you're looking at the truth table, you'll see that a 1 and a 0 is a 0. So the next operation is our OR operation. The OR operation will only require one of the input bits to be on in order to produce a 1 or an on value. So this, I think, is pretty self-explanatory. You can kind of see in the truth table. If you're still a little confused, don't worry about it. I think that some of these things will be better represented by actually using code and showing you how it works in the code session. So our XOR operator is probably one of the most confusing ones. And this operator, you can see on our truth table, is only on when only one of the inputs are on. If both inputs are on, this will produce an off signal. So you can see inside of our video, I'll play it once again, that we have a on and an on, and that should produce an off. Just like our truth table is evaluated, and you can check the rest. All these should match to the outputs of the truth table. So the last one is the NOT operation. This NOT operation is pretty simple. All it really does is invert the bits. So if you have a 0, your output will be a 1. If you have a 1, your output will be a 0. And you can see in this video, that is what we're trying to do. We have a binary value of 0, 0, 1, 1, and we should get an output of 1, 1, 0, 0. So the next operations that we have are shift operations, and we're going to start with the left shift. What the left shift is going to do, if you have a collection of bytes, so we'll just say 32 bytes because that's our typical standard size. When we shift to the left, we're going to take those bytes and move them down to the left n amount. And a left shift can truncate bits out of range. So if you think about it, if you have a range of 32 and you move more than that, it has the ability to truncate those and kind of throw them away. Now this depends on the type that you're shifting. It also depends on the compiler specific implementation. Here's the left shift operation example, and you can see that I'm using the binary.h file that I provided earlier in the lecture. And you can see, we'll just go through this first example. I would recommend typing this out and trying it for yourself. Again, we're going to go through some of this stuff inside the coding section, so that way you can see me do it live as well. So we have a variable x, which is an unsigned integer, and you can see in this line here that we are outputting, this is our binary representation, 32 bits, and when we print it out, that's the first line right here. And what we're doing is we're shifting it up 1, left shifting. And you can see it just pops in one more, and we can do it with 8 as well. There it goes. And then we shift up 31, we can see it go all the way to the end. And now when we shift 32, we can see it either wrap around, and we do 64, which is just 32 twice, and we see it wrap around again. Same thing happens for 17. Again, some of these operations are compiler specific, so if you're doing something and you are unsure of what would occur, it's better to just compile the program using the compiler that you choose, whether that's MSVC, TinyC, GCC, CLang, or Clang. Whatever you're doing, just compile it, output it, and see what the results are. It's usually the best way to test it. So the right shift operation works the same way as the left shift, except it goes in the opposite direction. So these, again, compiler specific implementation. And here again is the output using the print binary. We set a 1 and then we're shifting it to the right. So you can see when we shift it once to the right, it actually drops off and truncates, and it doesn't wrap around. So again, this is a compiler specific detail. It's going to, when you right shift, it's not going to allow it to wrap around to the beginning. This can also be type specific as well. I wouldn't get wrapped up in the details too much. Just know that you can always test this on your computer by writing a small program like this and seeing what occurs. So shifting overflows. So that is what I was referring to when I was saying that you can shift either 31, 32 bits out. This is referred to as a overflow. So again, depending on what variable type the overflow occurs on, it could tell the compiler how to handle this shift. So it can either tell it to truncate, wrap, or fill the overflow, with zeros or whatever value. It's always better to just test it out and see how it's working. So now I want you to try it out on your own. I want you to just come up with some examples that are similar to the ones that I showed you through this lecture. You can use the print binary function that I created for this course. I'll provide it to you inside of a header file, but we will be using that in our coding examples to make the output look a little bit nicer for us. Once you pause this video and try it out, go ahead and continue and move on to the code section where we can try some stuff out together. Okay, let's go ahead and start spending some time messing around with the binary H file provided in the lecture. So first thing that we will notice is the binary.h file is that we have a couple constructs inside of here that we're not too familiar with. We don't necessarily need to understand this file, but we do need to use it in the function that we provided, which is print binary. So this print binary function is going to output what we saw inside of the other lecture screenshots. So let's go ahead and start out by simply making our main.c file. Go ahead and open the main.c file, and let's go ahead and include our binary.h file int main. And first thing that we're going to do is what we normally do, is make a simple printf statement, hello world. And just in case you're wondering, if we go ahead and open up the binary.h file, let's move it over here, we can see that this file actually includes the stdio file. So when you think about it, when this does a direct replacement of this file, this will also include the stdio header. So this file will include this one, which then includes this. So if we go ahead and use our gcc -E main.c, we'll notice that if we just scroll up a little bit, that what happens here is that this code actually gets placed at the top. I'll go ahead and expand this. All of this is from stdio.h, which was included in binary.h. Now you'll typically see people say don't do things like this, but we're not really too concerned about that. We're just trying to understand how programs work in C right now and some specific details of the compiler, and we can discuss other semantics later. So anyways, we have a function print binary. That function we'll be using. we notice that we can at least get to the compilation stage of pre-processing. So let's go ahead and just compile the program, run the program. We have hello world. Everything's looking like it's running good. All right, so first thing we're going to do is let's make an integer, call it x, and then let's assign the value 256. Now, the reason why we're doing 256 is because it's an easy value to see in binary, and you will see that in a second. If we go ahead and say print binary and pass in x, save this, run it, we can see that we have a binary value here. So we're going to make two variables, x and y. We'll make this one 128. And what we're going to do now is we're actually going to write a bit of code here that's going to output our values, x and y. So that way we know what we're working with. So we have x, y. This is going to print out the x value. So we can just say, for this line, we can say printing x value. All right, and then we can swap this for printing y value. Go ahead and compile this, run it, and we can see that we have printing x value and we have it print out our 256 and printing y. So if we line these up, if you look at them, let's actually go ahead and create another file. Let's call it, actually, let's do something new that we haven't done yet. Let's redirect this output to a file. So we have done this actually, but we haven't done it with our own programs. So we can run our program, redirect it. Let's make this dump.txt. Let's go ahead and open up dump.txt, and you can see this is the output of our program. So let's go ahead and delete some of these lines here. And what we're most interested in is the number representation versus the binary. So you can see that these two numbers have this binary representation. And it's really just moving this one to the left or to the right, depending on which perspective, which number you're looking at. So what we can do is let's go ahead and let's write a little bit more of code examples to do an and some other bitwise manipulations. Let's do an and an or. So we're going to go ahead and print this out. We're going to say x and y. So we're going to print binary, and we're going to go ahead and do x and y. So what do you think this value is going to be? Now think about it. We just looked at the output in dump.txt. So if we take these two values and AND them together, we don't have any ones lining up with each other. So technically, this should come out with the result of 0. So let's go ahead and see. Let's compile our program, run the program, and yes, it does. So x and y is 0, and this is the binary for 0. So what do you think that the OR will be? Let's do an OR. So an OR, when we look at the output here, an OR will accept a 1 in either slot and then return that 1. So we should end up with a 1 in the 256 position and a 1 in a 128 position. So if we add those two together, that should be the result. So we should have a 1 in this position and a 1 in that position. Let's go ahead and compile the program. Actually, first we need to change this to an OR, and then let's clear our screen. Let's just recompile, even though we did that. A.out, and you see that's exactly what occurs. So we actually add 256 and 128, and we get this resultant value. So this is a bitwise and a bitwise OR. So we'll go ahead and do a XOR now. So let's do x XOR y. Now, before we do that, let's go ahead and assign our X value equal to, we'll say 257. And then our Y value is equal to 129. So we'll go ahead and reprint X and Y. Grab this guy, reprint X and Y, and then we're going to say X or Y. And then we'll print the binary. And it's going to be X or Y. Let's go ahead and clear the screen from the program. So what's interesting, and actually it's hard to see this, so we'll say X print binary and print binary. So let's go ahead and recompile this. Run. Okay, so now what I wanted to show you was the binary for these two results, and you can see we just added 1 to each of these values from our initial value. So we had 256, 128, now we have 257, 129, and all that did was just add a 1 in this position. So when we XORed those, you can see it's an exclusive OR, meaning that the two values that do not have 1 in each slot just returns a 1, but the 1 value and the least valuable bit, so this here, this position, actually gives us a result of 0, which if you're looking back on the truth table for an XOR is correct. So now that we have an example of an XOR, let's go ahead and move on to the NOT. So what I'm going to do for the NOT is I want to have a new value, let's say Z, and for Z, I know that the number -1 represents a binary value of all these bits turned to 1. So for instance, because this is a signed integer and not an unsigned, what's going to occur here is you're going to see when this number is printed out, it's going to be a very large number. It's because we're passing in this print binary statement a unsigned integer. So what we're going to do is we're going to say printf z %sign d, so that way we have some context of the actual value of z. And then let's go ahead and print the binary of this value. And then we will NOT it, which is our next step. But first, let's compile and make sure the output is exactly what we expect. So yeah, looking at Z, we say we have a -1, and you can see here when this call to print binary, it's a very large integer value, and that's because, again, like we've learned in other lectures, a value stored inside of memory is nothing more than binary. And what we do and what we tell the compiler, we tell the program how to interpret that binary. So in this instance, when I have this %sign d, it tells this statement to interpret it as a signed integer, which gives us back what we expect. But in this call, looking back at our binary.h file, we have an unsigned integer. And because a signed versus a signed integer interprets data differently, we get this weird large value, but the binary representation stays the same. So this might be a little confusing still. Don't worry about it. Watch the video a few times, practice on your own, and eventually you'll get this stuff. I know it's a little bit confusing at first, but anyways, let's go ahead and see what happens when we NOT this value. So if you recall, our NOT symbol is the tilde, this symbol here. So what we'll do is we're going to go ahead and say printf (z), so not z, and then we're going to print the binary. And thinking about it, like if we just NOT z, what does NOT do? So NOT should actually just invert all of our bits, right? So all of these 1s should turn to 0. So let's go ahead and do that. Save, clear, GCC may not see. Let's expand this because our output's getting kind of long. And there we go. So this is not Z. The number turns to 0 because we flip all of the bits to the opposite of what they are. I hope this is making a little sense. let's go ahead and do a few examples of left shift, right shift. And we're just going to go ahead and make our x value equal to 1. And we will print out our x value, x. And now what we're going to do is we're going to say x shifted, let's do, let's just say x shifted 16 to the left. So this is a left shift. So we'll just print, we're just going to print this out. Oops, sorry, I closed my files. Didn't mean to do that. We're going to go ahead and now print binary, and that will be x shifted to left 16. And you should see, let's do this, print. So we printed the value of x. We're going to go ahead and print binary x. And there we go. Okay, so let's clear the screen. GCC may not see, dot out. So you can see here, this is our x. When we set it to 1, 1 is in this position, and we shift it up 16 bits. It goes and moves towards this direction. Now what we can do is we can do the opposite. We can shift it to the right 16, and you will see what happens. So we shifted our value 16 bytes to the left and then 16 bytes to the right. So looking at this position, we had it here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I missed a few zeros, but that should be 16 bits upwards. And then we get rid of it and it truncates when we go to 16. So let's go ahead and do 15. And you will see that we should be back at our original value. Oops, I forgot to change this. So x is equal to 0. Did I forget something? So we shifted, so we should be at 1 here. So we shifted 16. Oh yeah, right. So the reason why is because actually what I showed you was incorrect. What we need to do is reassign x. So we can say x is equal to x shifted by 16, like this. And then we can print x, right? And then what we can do is the opposite now, which is x is equal to right shift of 16. And now we can reprint x. What was happening before is that we started out in this position. So when I was shifting 16 to the right, this was just truncating. So it wasn't wrapping around or anything. We were just losing data. So it's a good example of how the right shift can truncate data. Let's go ahead and run. /a. So here we go. So we start out with the number 1 here, which is printed out up in this line 38. We print out the binary, which is this call, and then we say, okay, we're going to shift it to the left 16. So we move over 16 units, and then we're going to shift it back to the right 16. So let's see what happens when we shift it x back over to, so we back at 1. So let's go ahead and say x equals x shifted up to 32 units to the left. So when you think about it, we're in the first position. So we should technically are going to go all the way to the end and then one more over the end. So we'll say, we'll grab this guy, print that out, and we're going to change this to 32. And we'll go ahead and print binary x. And let's go ahead and, you can even see this actually tells us that the left shift operator is greater than the with type. So we're going to get something called an overflow warning. So let's go ahead and run this. And you can see what happens is that the value is going to wrap around. So if I did 33 instead, go ahead and let's actually keep this example in. Redo this. So this is in the same position, right? This has not changed. So we're going to go ahead and do 33 instead. Watch what happens. Clear and GCC may not see. And you can see again, we get another overflow warning, but this time it moves one ahead. So we started in this position, we move all the way to the end, and then we go one more unit pass, and it wraps around. Now this is a different way of the way the right shift works. The right shift works is when you right shift off the end, it just truncates it with zeros. Zeros come in from the left. So a left shift, the way it's working is when we shift all the way towards the end and then we overflow to the end of our binary result, it actually will pop in that last value as we've tested here. Now, this is how this specific compiler handles overflows. Typically, people will tell you, this is a standard way of how overflows are handled, but it's really good to get familiar with the particular implementation that you're working with if you're working with a different compiler. Test these things out, try them out, use a binary.h file, dump them out, and you can look at the different binary and examine it and just play around with this stuff, get a little bit more familiar with it. It is kind of a difficult topic to comprehend at first, but it's really worth your time to intuitively understand these things. Great. Thank you for joining me on this lecture about binary or bitwise operations. Hope to see you in the next lecture.